Okay, so we all know that switching to renewables is like a big deal if we want to deal with climate change, right? And the Paris Agreement, that goal of keeping things below 1.5 degrees Celsius, that just really shows how urgent it is. We're like teetering on the edge with some of these climate tipping points, like the ice sheets melting and the forests dying off. But here's the thing, even if we went completely renewable, there are these tricky sectors, what they call hard to abate sectors, like shipping and aviation. It's not like you can just plug in a giant battery and call it a day.
Right, exactly. And that's kind of where e-fuels and e-chemicals enter the scene. You can basically think of them as like carbon neutral alternatives that are produced using renewable electricity. And what's particularly interesting, for you, learner, to think about is that a lot of these Sunbelt countries, the ones with tons of sunshine and available land, well, they have this huge potential to not just produce these e-fuels and e-chemicals, but to become like major exporters.
Okay, so let's dive into that a little more. We've seen studies on how these sunny countries could become like global energy powerhouses, right? But today we're digging into a really cool angle. We're looking at the techno-economic impacts. So basically, the tech stuff and the money stuff of these countries also doing carbon dioxide removal, but within their own borders.
Yeah, it's like a double whammy in the fight against climate change, right? They'd be supplying clean energy and actively cleaning up the mess. So to really wrap our heads around all this, we're focusing on Egypt as a case study, a great example of a Sunbelt country with a good chunk of land.
So today, learner, we're going to break down this study for you called, get this, Analyzing the Techno-Economic Impact of E-Fuels and E-Chemicals Production for Exports and Carbon Dioxide Removal on the Energy System of Sunbelt Countries case of Egypt.
Yeah.
It's a bit of a mouthful, but it gets into the nitty-gritty of what happens when a country like Egypt tries to juggle three things: exporting clean fuels, removing CO2 from the air, and going 100% renewable for their own needs.
What's really neat about this study is that it doesn't just look at one possible future. It lays out four different scenarios for Egypt. One is all about exporting e-fuels and e-chemicals. Another focuses just on carbon dioxide removal. And then there are two that combine both, but they look at different ways to do that CO2 capture. And they compare all of these to a baseline scenario where Egypt just goes 100% renewable for itself. And just a heads up, what they found is actually pretty positive for Egypt and maybe other countries in similar situations.
Okay, this is where it gets good. Let's start with the overall energy demand. We're talking about carbon dioxide removal on like a global scale.
Right.
The study looked at Egypt aiming for 5% of the global capacity, starting in 2035. Well, by 2050, the energy they'd need is way more than if they just went 100% renewable for themselves. Their total primary energy demand, or TPD, it would be 2.1 times higher. That's huge. So if a country wants to be serious about carbon removal, we're talking about a massive energy infrastructure build-out.
Yeah, that's a significant jump in energy needs for sure. Now, if we compare that to Egypt supplying, say, 10% of Europe's demand for e-fuels and e-chemicals, their TPD is still higher than just going renewable domestically, but not as much. It's about 1.3 times higher by 2050. So exporting clean fuels takes more energy, but tackling carbon removal on a global scale, that's a whole other level of energy commitment.
And when you combine both, exporting those e-fuels and e-chemicals and removing CO2 well, the study looked at two ways to do the CO2 removal. One uses concentrated solar thermal, or CSP, for the CO2 capture. With that, the total energy demand skyrockets to 2.3 times the domestic scenario by 2050. But if they use solar PV and heat pumps, it's a bit lower, at 1.8 times. So the choice of technology for carbon removal, even that has a big impact on the overall energy picture.
And the key here, learner, is that all that extra energy demand in the CO2 removal scenarios, it's mainly because of the heat needed to capture the CO2, especially if you're using direct air capture, or DSC. That's a technology that literally sucks CO2 right out of the air, and it needs a ton of heat.
So let's shift gears and talk about how all this energy gets generated, starting with electricity. If Egypt just focused on its own transition to 100% renewable energy, or even if they just did the CO2 removal, solar PV would be the big kahuna. By 2050, it generates something like 94% of their electricity. Wind power would be a much smaller player, like around 5%.
But then you look at the scenario where Egypt is exporting e-fuels and e-chemicals, and wind power starts to matter more, coming in at around 14% of the mix. And it makes sense, right? Wind is a bit more consistent than solar, which is important when you're talking about industrial processes that need to run all the time to make these synthetic fuels. And the scenarios where they do both exports and CO2 removal, they still rely heavily on solar PV, but wind power picks up there too, more than in the domestic-only case. It seems like when a country takes on a bigger role in global energy, a more diverse renewable portfolio just makes sense.
Now, heat generation, that's a different story. In the domestic and the e-fuel export scenarios, heat generation goes up, but not drastically. It's mostly for industrial processes.
Yeah.
But when you look at the CO2 removal scenarios, whether it's alone or combined with exports, the increase in heat generation is crazy. It's more than 8 times higher than the domestic scenario by 2050, just in the CDR-only case. That's a whole different ballgame.
And remember, learner, that goes back to the heat needed for direct air capture. And what's interesting is how they supply that heat. One option is concentrated solar thermal, or CSP, which directly provides high temperature heat. The other option is using solar PV to generate electricity and then using that to power heat pumps to make the heat. And what they found is that the PV battery heat pump combo actually uses less total energy overall. So even though DSE needs a lot of heat, how you generate that heat makes a difference.
Okay, so with all this renewable electricity and heat coming online, storage becomes a big deal. You have to be able to keep the lights on, even when the sun isn't shining or the wind isn't blowing, right? The study found that the exact mix of electricity generation, like how much solar versus wind, really impacts the types of energy storage you need, like batteries and thermal energy storage.
Exactly. If solar PV is the main source of electricity, you need more batteries to cover those times when the sun dips below the horizon. Makes sense, right? But if you have a decent amount of wind power in the mix, you might need fewer batteries. That's because wind and solar often work well together. When the sun's down, the wind might be picking up. That natural balance helps keep the energy flowing steadily.
And then you've got the CO2 removal technology itself, which also affects storage needs, right? When they modeled CO2 removal using CSP, it resulted in a lot of thermal energy storage. That's because CSP can store heat directly, for example, in molten salt. That means you don't need as much hydrogen storage, which is another way to store energy for longer periods.
Right. It's a key point for you to consider, learner. Thermal energy storage acts like a buffer, allowing the CO2 capture to keep chugging along even when there's no direct sunlight. It's a way to disconnect the energy supply from the immediate demand of the DX process, which makes the whole system more reliable and might even mean needing less of those other more complicated or expensive storage solutions.
So let's get specific about Egypt. Where in the country should they put all these e-fuel plants and CO2 removal facilities? It sounds like you really need to go where the renewable energy is strongest.
You got it. The study really stresses the importance of what they call full load hours, or FLH, for renewable energy tech like solar PV, wind, and CSP. Basically, FLH tells you how many hours per year a power plant can operate at its full potential. Areas with higher FLH are going to have lower costs for generating electricity and heat.
And the study pointed to Upper Middle Egypt and Upper Egypt as the best spots, didn't it? Those areas have higher FLH for both solar and wind, which means lower levelized cost of electricity, or LCOE, and lower levelized cost of heat, or LCOH.
Right on. Since making e-fuels and e-chemicals takes a ton of energy, especially electricity, those regions with all that renewable potential are perfect for export-oriented production. And because direct air capture needs a ton of heat, the lower LCOH in Upper Middle Egypt and Upper Egypt makes them perfect for CO2 removal facilities. Actually, the study found that in the scenarios with CDR, more than 96% of the CO2 removal capacity ends up in those two regions. It shows how important it is to figure out where the best resources are when planning these huge energy and climate projects.
Okay, now for a twist you might not expect, learner, the cost of all this. Turns out, providing carbon dioxide removal could actually be good for Egypt's wallet.
It's pretty surprising. If Egypt just focused on offering CDR services to the world, their LCOE, LCOH, and even their overall annual costs would be lower than if they just went 100% renewable domestically. That's not what you'd expect, right? It suggests that getting involved in global climate solutions could actually have direct economic benefits.
Now compare that to Egypt, only exporting e-fuels and e-chemicals. In that case, their annual costs are higher at first, though their LCOE and LCOH do go down a bit early on. So exporting clean fuels has some cost benefits, but it doesn't seem as immediately helpful to their own energy system as carbon removal.
But get this, the study found the real magic happens when you combine the two. When Egypt does both exports and CDR, they see lower LCOE and LCOH throughout the entire transition. And what's even cooler is that by 2050, this combo actually results in the lowest overall annual costs compared to just going renewable domestically. And here's another interesting bit. It doesn't really matter if they use CSP-based or PV-based CO2 removal for this combo. The economics are pretty similar.
Now, what about the cost of removing the carbon itself? The study looked at the levelized cost of CDR, or LCOCDR.
Yeah, and they found that the LCOCDR is lowest when you do CDR with e-fuel and e-chemical exports using CSP, and they actually compared their LCOCDR numbers to other studies. There were some differences because, well, different studies model things differently, like how much detail they include about specific locations and whether they factor in the cost of transporting and storing the CO2. But overall, their findings were in the ballpark of what other research has found. That makes their results pretty solid.
And here's another interesting point about costs. The study found that producing lots of e-hydrogen for export would actually make it cheaper overall. And that would make it more affordable to use e-hydrogen within Egypt too, across different sectors. It shows how focusing on clean energy exports can have a ripple effect and make things better at home too.
You're right. Producing more of something, like e-hydrogen, can make the cost per unit go down, which is great for everyone. And their findings about e-hydrogen prices were pretty similar to other studies from the MENA region, suggesting that the area has a real advantage in green hydrogen production. But they did point out that some of the other e-fuels and e-chemicals, things like e-FTL, which is like synthetic kerosene, e-methanol, and e-ammonia, were a bit pricier in their study compared to some others. That's probably because their model is more comprehensive, including costs from things like existing infrastructure and using regional averages instead of focusing on specific ideal locations. It gives a more realistic view of the overall costs.
So we see some real potential economic wins for countries that take on this dual role. But what about the practical stuff? How much land would all those solar panels, wind turbines, and CSP plants take up? And what about CO2 emissions during this transition?
Land use is a big deal whenever you're talking about renewable energy. The study was very careful in calculating how much land would be needed under each scenario. They look at it as a percentage of Egypt's total land area. For just the domestic 100% renewable transition, it's about 1.6%. And even in the most ambitious scenario, with both exports and large-scale carbon dioxide removal, it only goes up to about 3.6%. That's not a huge amount of land relative to the size of Egypt, so it's unlikely to cause too many problems.
That's good to know. Now about emissions. It turns out that in the scenarios with e-fuel and e-chemical exports, the total CO2 emissions over time are a bit higher than if they just went renewable domestically. Why is that?
Well, the model they used had a built-in limit on how fast they could build new renewable energy capacity, no more than 4% growth per year. So to meet the early demand for e-fuels for export, they had to rely a bit on existing fossil fuel plants. The researchers said that if they relaxed that limit, or if there were policies to restrict fossil fuel use specifically for e-fuel production, those extra emissions could be avoided. It just highlights the need for smart policies to make sure that the push for clean energy exports doesn't actually slow down the overall shift away from fossil fuels.
But then there's the carbon dioxide removal itself,
Yeah.
and that seems to be the real game changer, right?
Yeah, for sure. The study found that when you add in carbon dioxide removal, Egypt's energy sector would hit net zero emissions between 2035 and 2040. And by 2050, they'd actually have negative emissions. That means they'd be taking more CO2 out of the air than they're putting in, and at a rate 10 times higher than their 2020 emissions. That's a massive shift, and it shows the huge potential of doing both renewable energy and carbon removal.
The study also did a quick comparison of direct air capture with other carbon dioxide removal options.
Yeah, they talked about the differences between DACS, direct air capture with carbon storage, and BACCS, bioenergy carbon capture and storage. BCCS basically means growing plants for energy and then capturing the CO2 when you burn them. But it uses a lot of water, which is a problem in a place like Egypt. They also mentioned using desalination plants to make fresh water for growing trees in dry areas. That's called desalination-based afforestation, and it could work well in northwest Egypt. But even though trees are good for lots of things, the study suggests that DICCS might be a better and more scalable option for CO2 removal in Egypt, especially given the limited land and water.
So, Lerner, what have we learned from all this? What does it mean for Sunbelt countries and for anyone who cares about energy and climate?
The study makes a strong case that Sunbelt countries with the right resources should go for both carbon dioxide removal and e-fuel chemical exports. It's the best way to make their energy systems more efficient, use less energy overall, and save money in the long run. These countries are in a great spot to be leaders in the fight against climate change.
And they have options for the CO2 removal tech, both CSP and solar PV seem to work well. That gives them flexibility to choose what's best for their situation.
Exactly. They can tailor their approach to their own needs. The study also suggests that taking on both roles, clean energy exporter and carbon remover, would speed up the adoption of renewable energy, boost innovation in projects, and make their workforce more skilled.
It really shows the importance of developed countries and Sunbelt countries working together. The developed world needs those clean fuels and climate solutions, and Sunbelt countries can provide them.
Right. It could be a win-win. They can both achieve their climate goals and make sure everyone has reliable energy.
Let's recap, learner. We saw that doing both carbon dioxide removal and e-fuel chemical exports can actually be good for the exporting countries. It helps their own energy transition and can boost their economies. We talked about the potential of specific regions within Sunbelt countries like Egypt to become hubs for clean energy and carbon removal. And maybe most importantly, we saw how these countries have a real shot at leading the way in solving the global climate challenge.
This deep dive into that study, analyzing the techno-economic impact of e-fuels and e-chemicals production for exports and carbon dioxide removal on the energy system of Sunbelt countries' case of Egypt, really flipped the script on us. It showed us that what might seem like an extra burden, providing those global climate services could actually be a powerful driver for a strong and successful domestic energy transition, opening up exciting new economic opportunities along the way.
So here's something to chew on as we wrap things up. What kind of international partnerships and creative policies do we need to really unlock the potential of Sunbelt countries to tackle climate change and create a secure, sustainable energy future for everyone? It's a big question, and maybe they'll spark you to do some digging of your own into global energy transitions and those awesome carbon capture technologies. Thanks for joining us for this deep dive.